Hello and welcome to another episode of EnVisioneering Exchange, the podcast where industry leaders discuss the most important topics in sustainability, climate change, buildings, and urban efficiency. I'm Vic Marinich, Global Marketing Director at Danfoss, and I'm excited to be the host of this podcast. You can subscribe to our show on Apple Podcasts, Spotify, SoundCloud, or wherever you get your podcasts. Today, we're glad to have Ron Domitrovic from the Electric Power Research Institute, or EPRI, on the show to bust some myths about heat pumps. Ron manages the Grid Edge Customer Technologies Program at EPRI, a nonprofit energy research and development organization that works with industry and policy experts to enable clean, affordable, safe, and reliable access to electricity for the public benefit. Ron, welcome back to the show.
Thank you, Vic. It's good to be here.
We had such great feedback the last time you were on the show talking about heat pumps. We thought it'd be fun this time to maybe get a little less into the technical details, but let's do some myth busting around heat pumps for nerds like us who like to talk about heat pumps. Before we dive right into the myths, though, maybe we kind of set a foundation. So first things first, let's start with the basics. Why should we even care about heat pumps, and why are they considered a promising technology for decarbonization?
Yeah, so why should we care about heat pumps? So there are a couple of reasons. One is that there's a societal push to decarbonize and to reduce and ultimately stop the use of fossil fuels. And so we need options for how we maintain our comfort and in hot water and so forth. And the heat pump is a wonderful technology for allowing that to happen by using electricity and the like. But then there's another reason is simply that a heat pump is an elegant, efficient technology that allows for the movement of heat very easily and very effectively with relatively little power input. And, I know we're not going to dive deep into the technology, but there's a distinction we should probably make between burning a fossil fuel and then using a heat pump, which is a heat engine. And so without giving a whole lecture on thermo, the difference is really that when you burn a fossil fuel, it's a thermodynamic process. And so you burn methane, for instance, and it combusts and it produces exhaust that is very hot. So, 2,800 degrees Celsius is a very, very hot. But it's kind of just a continuous process. You burn it and you get it. And then you can use that heat however you like. You can use that heat to heat something that has to get very hot, or you can use it to heat something that doesn't need to get that hot. You can use it to heat air. You just blow a lot of air over that hot gas and it warms partially. So you have a lot of flexibility with just burning combustibles, but it's a process. And so it happens once and it's done and it exhausts out the other end. A heat pump is a completely different animal. It's a thermodynamic cycle. And so you use a fluid, a refrigerant that we all know, and it cycles through multiple processes to move heat rather than create heat, as the combustion process does. And so there are some rules that govern how that can happen. And one of them is that the closer the temperatures are of the place you're moving the heat from to the place you're moving the heat to, the closer those temperatures are, the more efficient that heat pump process can happen. And so the details of the heat pump and the application of the heat pump are all wrapped up in what is the temperature lift that you're trying to create to happen. So if you're trying to heat a house to 70 degrees and it's 30 degrees Fahrenheit outside, that defines that lift. But the beauty of it is, in the range of temperatures in which we're operating, typically for home heating, for building heating, for water heating, even for many industrial processes, those temperatures are favorable enough that the heat engine or the heat pump can move that heat very effectively with relatively little energy input to the system. So that defines the coefficient of performance, or the COP. And so for a small unit of energy input, we can move a relatively large amount of heat for our purposes. So that's why we're interested. One, because it's a very effective tool for heating a variety of things when you don't have fossil fuel at your disposal. And two, it's a very effective way to do it even if you do have fossil fuel at your disposal, because it moves heat very, very efficiently.
It's important to note too, right, that it's not like we're just developing heat pumps because of all the recent focus on decarbonization and climate change. Heat pumps have been around a long time, right? And as you mentioned, right, heat pumps are a technology, not a process. So as a technology, they can get better and better and better, right? We can continue to improve on those technologies. And that's, I think, kind of gets to the core of why we have these myths, because a lot of people, I know I looked at a heat pump 35 years ago when I was living down south, and that's not the heat pump that I have in my house today up here. So as a technology, it's come quite a long way. But now, as we speak of heat pumps, a lot of different lingo getting thrown around. We have ground source, we have air source, we have water source. Can you maybe explain a bit what's all that mean? Is one better than another?
Well, depends on which manufacturer you ask. But no, I mean, they're the same general approach. So remember that it's a cycle. So you're taking heat from one place and you're moving it to another place. So you have a heat source and a heat sink. And you're usually taking heat from a colder place and you're delivering it to a warmer place. That's why you're pumping it. You're pumping it up to a higher temperature. As I mentioned, you're pursuing favorable temperature conditions that allow you to do that very efficiently. And so, no, an air source heat pump simply means that the source that you're drawing heat from, the cold place, is air. So outdoor ambient air, typically. And then a water source heat pump or a ground source heat pump says that it's deriving that heat from the ground or from water, maybe a lake or something like that, or a process, for instance, an industrial process. So that's really all that means. And so you can take heat from one place, air, water, ground, and you can deliver it to another place. Now, we're usually delivering it to things like air and water, but again, in an industrial process, you might deliver it to something else, some other medium. But so that's really what that means.
Mm-hmm. Okay. So again, it sounds pretty flexible. You can take the heat from lots of different places and put it, as you said, directly into the air or into water, a loop that's going to get distributed, or an industrial process. We talk heat pumps, right? Sometimes you'll hear, especially in the Northeast, right, that you can use a heat pump to replace a boiler, right? So the heating in the home. But then sometimes you hear you would use the heat pump and replace your air conditioner and then your furnace. So are all heat pumps reversible? Can they all do heating and cooling, or are there some just heating, or what's the difference there?
Yeah, so I guess in the purest sense, the heat pump is the broader class of heat engines that follow a sort of a certain thermodynamic cycle. And it is a device, as I said, that uses thermodynamic processes to take heat from a cold place and deliver it to a hot place. So depending on which direction you want the heat to go, then that kind of tells you whether it's a heat pump for heating or whether it's an air conditioner or a refrigerator. So think about your home refrigerator. It is taking heat from the inside of the box, which is cold, and it's delivering it to your kitchen, which is a little bit warmer. So it's a heat pump, but it's delivering the heat into your space. Whereas the opposite would be maybe a heat pump water heater, which is taking heat from, let's say it sits in your basement. So it's taking heat from your ambient air in the basement, and it's pumping it up, and it's delivering that heat to the warmer water inside the storage tank. So it really is just a function of the direction. But many, many heat pumps, especially, for instance, residential split systems, are both heating and cooling capable, and they can be switched. So their direction can be reversed. So that in the summertime, you're taking heat out of your interior space and delivering it to the outside, whereas in the wintertime, you're taking it from the cold outside and you're delivering it to the warmer inside. And that's just a function of how the refrigerant is flowing, and you can create that reversal with valving and so forth.
I think clear there's a lot of benefits to applying heat pumps commercially and residentially, right? And we're about to go through some myths that we think that exist in the market today, right? Really exposing how far heat pumps have come. But does all this mean that heat pumps are the one only final solution that we're ever going to need for heating?
Well, I wouldn't say they're the one and only. They are a very good solution, and they have the potential to be a very good solution. I think there will always be a need for specific temperature or characteristics that necessitate a fossil fuel or combustion, I should say. It doesn't have to be a fossil fuel, but it could be hydrogen for that matter. So, yeah, if you need very high temperatures, or you have confined space, or you have other limitations, then combustion is very viable. But heat pumps in general can be created and engineered for a very wide variety of thermal applications.
Yeah, so definitely a significant tool for decarbonization. So let's jump into the myths here. We got myth number one: heat pumps just aren't comfortable. They provide cold air.
Yeah, that's an old one. That's an oldie but a goodie.
Yeah.
Traditional heat pumps, what I call, if we think residentially, the single speed heat pump from 20 years ago or so, or even 10 years ago, they were designed as air conditioners. So they were designed as air conditioners, but it was realized that you can just reverse the flow and make it into a heat pump. But the approach was to design for the air conditioning load, reverse the system, and then you get what you get in the wintertime for heating, and then you just supplement that with something else. You either supplement it with natural gas burning or with electric resistance or something else. But there's some nuances of operation that when the heat pump was operating, sometimes it delivered air that was, significantly colder than what a gas furnace would produce, 10, 20 degrees colder. And so people had the impression that it's blowing cold air. It's not. It's blowing air that's warmer than the ambient, and it is producing heat, but it has that impression. Then there's a secondary feature, which is the need to defrost the outside coil, and that can often cause shorter bursts of what appears to be cold air. So, okay, that's the old style. The newer style systems, especially the variable speed systems and variable capacity systems, have really engineered that problem away. And they can adjust the compressor speed and the flow of refrigerant and the fan speed and the flow of air to really deliver whatever air temperature is desired or is appropriate. Now, going to too high an air temperature unnecessarily decreases the efficiency of the system. So you want to be at a reasonable temperature that's efficient, but is still, doesn't give the appearance of being cold, but very, very possible with modern day systems.
Mm-hmm. Myth number two, that all sounded fantastic, Ron, but of course that's really just for like mild and intermediate climates, right? They really don't work so well in cold climates, right?
Well, you're a real skeptic, aren't you, Vic?
Absolutely.
So again, it comes back to what a heat pump is. It's this engine that is taking heat from a cold place and delivering it to a warm place. And I said they follow some rules. They have to follow some rules of physics. And one of those is that the higher that temperature lift is, one, the lower the efficiency is, meaning you have to put more power in to make that happen. But two, is that the lower the capacity is. So the lower the heat transfer is from the source to the sink for a given amount of fluid flow. And so when you engineer a system, you have to take all of that into consideration, but it's not that big a deal in that you just have to engineer a system to operate in all the expected operating conditions, so that if you know that you're in the northern US and you're going to see temperatures of 0 degrees on a regular basis, that's fine. You just have to design the system and choose the system to match those capacity requirements. So, myth that has some foundation in the way systems have been put in the past, but a very easy solution from an engineering standpoint.
Mm-hmm. Yeah, and I think you brought up a really good point in that first myth that 20 years ago or 30 years ago, whatever it was, we were really talking about air conditioners running backwards to get heat, whereas today there's really a lot of focus on making sure we're getting, good temperatures, good efficiency, good performance out of the units running in heating and in cooling mode. And we can see that in the minimum efficiency requirements too, right? It used to kind of be cooling and you get what you get for heating. And today there's some pretty strict requirements for both heating and cooling mode. So our myth number three, the heat pumps are really only going to be effective and efficient if you've got, a new home, you're very well constructed, very well insulated.
Well, again, two different problems. That's sort of a conflation of two different things. A bit like the last myth, where they only work in cold or warm climates. But so if you have a very poorly insulated house, which you shouldn't have, but if you do, it has a certain load requirement. So it has a certain thermal requirement. Well, you can design a heat pump. You can engineer a heat pump to match that load. Now, that is not the most efficient way to do it. You would prefer to have a well-insulated home, just like you would for a gas furnace. So if you don't have a well-insulated home, then you're unnecessarily using energy to heat that home, whether with a gas furnace or with a heat pump. So I would say you always want the well-insulated home, but that does not preclude you from using a heat pump successfully.
Yeah, very good point. Good. Now we get a bit into the heat pumps themselves. So myth number 4, heat pumps are expensive to operate and they require a lot of maintenance.
I would just say wrong and wrong.
Yeah.
They're actually, if they're a high efficiency style, they're actually relatively inexpensive to operate because you're putting very little energy in to move a lot of heat. And you can have ratios upwards of 4, 5, 6, even 7 for certain processes, where you're putting in 1 unit of energy and getting 5 or 6 units of useful heat movement. And so that's a very, very efficient way to heat. And so I would say, no, they are very efficient to operate and generally low cost. In terms of maintenance, they're relatively simple machines. They have 4 primary components. And, if well designed, and most of them are, and well engineered, they tend to last quite a while. So there is maintenance that's required, but it's the same sort of maintenance that's required for a gas furnace. Like you have to change the filters and that sort of thing, but it shouldn't be substantial.
Just wondering, when you talk about expensive to operate, do you think that may come from the foundation too that historically in the U.S., right, we've had very cheap natural gas, right? So the furnace could be expensive. And so you're switching fuels. It's not just about the efficiency of the unit itself. It's about the price of that the utilities are charging you for your gas and your electric as well, right? But I think that's kind of going away as well these last few years.
Well, that is a very good point, and that is certainly a consideration. And that made me think of another one, is that with older heat pumps, and to a degree still some that are installed today, they often will have electric resistance second stage heat acting as that backup for very cold conditions. And when that electric resistance heat is triggered, it operates at a very low coefficient of performance, and it can be very costly to operate. So I think that has probably unfairly labeled heat pumps as using a lot of energy or using a lot of electricity and thereby costing a lot. But the newer systems are moving toward where you do not need that electric resistance backup. It will be fully carried by the load is fully carried by the heat pump, and the operating cost is significantly lower.
Right. So the technology is also driving that cost issue away. Myth number 5, heat pumps are complicated and expensive to install.
Well, installers might like you to think that,
Yeah.
but they're usually modular. They're like your air conditioner, and they in the residential space at least, and I'll kind of stay focused on that. They come kind of in 2 flavors. They come in a split system and in a packaged system, and there are different flavors of split systems and so forth.
Sure.
But they're really basically the same system that has been installed as an air conditioner for many, many years. And though the newer systems are maybe slightly more complex and require a slightly more educated installer, they're not substantially different. So no, I don't think it's really any more complicated to install a high-end heat pump or a sophisticated heat pump than it is an equivalent gas furnace.
I think if you walk past the typical home in the U.S. and they had a split system, you can't look at it and say, oh, that's a heat pump or that's a cooling only unit, right? If you pulled the top off and looked inside and checked to see if there's a valve or maybe an accumulator or something, but if you're walking past a house, they look the same, right?
Yeah, a trained eye might be able to tell subtle differences, but you're right. Most people know.
Myth number 6, then, heat pumps are noisy.
Well, some will argue that furnaces can be noisy too. But again, I go back to the older style heat pumps. or air conditioners. They have a fan on the outside of the house, and that fan is typically on off. And then when it's on, it's making noise, and when it's off, it's not making noise. So, but the same is true on the interior. There's a blower on the inside. When it's on, it's blowing air, and if the ductwork is sized incorrectly, it can be noisy. But again, with newer systems, with the more advanced variable capacity systems, many of the fans and the blowers are variable speed, and they tend not to run at full RPM. They tend not to run at full speed, and therefore are quiet most of the time. And not only that, but the manufacturers have designed blowers and fan blades that are much quieter than the previous, the old style stamped metal. And so I think the noise impact of heat pumps and air conditioners has dramatically improved over the last decade or so.
I guess you probably hear the inside more. And if that's the case, if you're moving air, whether it's a furnace or a heat pump, you've probably got a similar blower right inside. So I don't see how you could be louder with a heat pump. And then outside, I would imagine if you're heating, you don't have your windows open or anything else, right? And if you have a reasonably insulated house, then the outside noise is probably pretty tough to pick up also. But yeah, that could be one difference. A furnace doesn't have an outside section, right? Or a boiler doesn't have an outside section to worry about. But for sure, inside, I don't see a big deal. Yeah. Myth number 7. So, okay, we've talked about a lot of the great things with heat pumps, and we talked about the old heat pumps, but are we really there yet with these new heat pumps? Are these efficient, quiet, able to work in cold climate heat pumps? Are they available in the market today, or are we talking about kind of what we see in the future?
It's a little of both. So certainly they are available in the market. They tend to be the emerging technologies, not as widespread in the typical installation. So what drives the typical installation still tends to be the federal minimum requirement. And that can still be satisfied by single speed equipment. And so that still tends to have the flavor of the old style heat pump. But we see that changing relatively rapidly. And there is greater and greater adoption of the variable capacity systems each year. We see more and more. And so, within a number of years, decade, whatever, we think that's going to be the predominant style.
Yeah, I always imagine kind of a line somewhere around cutting across the country that's slowly moving north, right, where we talk about significant heat pump penetration, right? It's slowly going further and further and further north, where, maybe some years ago you wouldn't consider it, but today it can easily become the norm, right? So heat pump technology, the technology in and of itself, how do you see that as kind of a natural progression when it comes to just resource utilization in general?
Heat pumps allow for very effective use of resources. So what do we want? We want comfort. We want hot water. We want a process to operate. And that has requirements. It has thermal requirements. Well, ideally, you would achieve those thermal requirements. So you would achieve the comfort in your home with as little energy expenditure as possible. And so how do you do that? You do that with very good insulation, and you do that with a machine that allows you to heat your home with as little input as possible. And that's what a heat pump allows. It allows for that very, very, what I call judicious use of energy to provide the comforts or the processes that we're after.
And I think that's an important point, right, that we want to drive home, because it's not that suddenly, right, there's going to be whatever government mandates about switching to heat pumps and that kind of stuff that's making this shift, right? I mean, you as a homeowner or as a business owner, you want to minimize your energy usage, even if it's purely for financial reasons, right? And as heat pumps are getting better and better and better, they just are the best choice in delivering that heat, right? It's not a mandate that if you could care less about global warming and all the other stuff, heat pumps are becoming to the point where they are the right investment to make in your business or in your home, right?
Yeah, I think it's getting to that point. And I liken it somewhat to the LED bulb. And I forget if I mentioned this on the previous podcast, but the LED bulb is now the default bulb that we go to for lighting because it's a very good product. It's actually a better product than an incandescent in most situations. And so we naturally want to use it. And so I think heat pumps are moving in that direction. And as the manufacturers and developers hone the technology, it's only going to get better.
Mm-hmm. Yeah. Of course, you could use that incandescent bulb for heating too, if you needed, right?
So you could. That's right.
So, all right, let's go with our last myth here, and that is that heat pumps take up a lot of space.
Well, again, I'll stick to the residential style. So on the inside of a home, they really take up no more space than a furnace. And in fact, they have a variety of configurations that might even allow them to reduce the space that they take up. So you can have wall-hung indoor units, you can have ceiling-mounted indoor units, you can have centrally ducted like a gas furnace units. Now, one would make the argument, well, you can have baseboard heat or you can have in-wall heat and so forth. So I would say on the interior of the house, it's a wash. And then on the exterior of the house, yes, you do have to have a condensing unit, or the outdoor unit, as it's called. So that is a space requirement. But generally in U.S. households, that's not an issue. Where that does become a bit of a concern or an engineering challenge is in larger buildings, especially tall buildings, skyscrapers, where you may not have roof footprint, or you may not have a place to put the heat exchanger surface that you need to make a system like that work. And that's why that's the frontier of development right now, is how to make heat pump systems for the more difficult to solve building problems, which would really be densely packed tall buildings in cold climates.
Mm-hmm. And I guess then we would be talking about a water-to-water unit, right? Because if you've got an air-cooled chiller that, let's say now you make reversible, maybe you do need some more surface area on the heat exchangers, right? Depending where it's installed. But if they're already on the roof, the challenge could be if it's water to water and sitting down there in the basement, then you're going to have to find a place to put all that dunnage up on the roof, right?
Yeah, that's where there are all sorts of interesting engineering solutions to it. So you can use ground source, you can use wastewater source, you can use lake source, river source, et cetera, if you don't have the ability to use air. So yeah, many options.
Yeah, and that's a whole separate podcast, how the heat pumps can be used to take advantage of some of that low-grade heat to boost up in the building. So if you have, you said wastewater and all those things that today would just get dumped down the drain, or hot air that would get blown out to the atmosphere, we can use the heat pumps to recover that and to improve the efficiency of whatever you're building or your process even more. But yeah, kind of the sector coupling, that's, I think, a whole episode on its own. So maybe we just end it there with you for today, Ron. So I appreciate it.
Thank you very much, Vic. Always a pleasure.
That's it for this episode of EnVisioneering Exchange. I'd like to thank my guest, Ron Domitrovic, Program Manager at EPRI, for joining us. Don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, SoundCloud, or wherever you listen to podcasts. Lastly, if you've enjoyed this episode, don't forget to rate, review, and share it with your network. Thanks for listening, and talk to you next time.
This podcast is for information purposes only. The views, information, or opinions expressed during the EnVisioneering Exchange podcast series are solely those of the individuals involved and not necessarily represent those of Danfoss LLC and its employees. Danfoss LLC is not responsible and does not verify for accuracy any of the information contained in the podcast series available for listening on this site. This podcast series does not constitute professional advice or services. This podcast, including Danfoss LLC and the producers, disclaim responsibility from any possible adverse effects of information contained herein. Opinions of guests are their own, and Danfoss LLC in this podcast does not endorse or accept responsibility of statements made by guests. This podcast does not make any representations or warranties about the guest qualifications or credibility. Individuals on this podcast may have a direct or indirect financial interest in products or services referred to herein. This podcast is available for private, non-commercial use only. You may not edit, modify, or redistribute this podcast. The developers of the EnVisioneering Exchange podcast site assume no liability for any activities in connection with this podcast or for use of this podcast in connection with any other website, computer, or playing device.